So good morning, all. I have this really fancy title, right? Senior Water and Climate Research Scientist and Scholar. And my wife regularly informs me that only 3 words are actually true. She says I work on water and climate, and of course, I'm really senior. So before I start, I just want to thank you all for what you do. I mean, you know this. You are working on the single most important issue facing humanity, and you're doing it on your free time. You're doing it for free. I mean, thank you. So I'm going to talk today about water and climate change, and this is basically all my work. This is the Rio Grande River in New Mexico. I'm not going to talk much about it, but this is a series that the Washington Post is now doing on areas that have raised in temperature 2 degrees Celsius or more. And how many of you, I think you're all from Colorado, right? Anybody not from Colorado in here?
Arizona.
Oh, Arizona, interesting. Okay, all right. I'm not going to talk much about the Rio Grande, but I'm going to talk a whole lot about the Colorado River. So I think all of you know the climate change, water change connection. If you don't, I'm going to pound it into you by the end of this talk. It's going to change water supplies and demands significantly. Colorado River climate change is already impacting the Colorado River in major ways. And as the 21st century unfolds, it's going to get a whole lot warmer. We know much less about precipitation. We're likely to see flow reductions in the Colorado River and any rivers in the southern portion of the American Southwest. We now are using a term called aridification, right? When you've had a drought for 20 plus years, you can't call it a drought anymore. You have to come up with another term. Expect weather whiplash, and we saw that in 2019, and we're going to see it more going forward. This is an image from a Routt County ranch near Steamboat, and it's the snow melt-out day of a hay meadow. If you're in the top part of this graph where the green numbers are, that's actually late melt out, so into May, and then the red numbers are early melt out. And you can see the most recent red numbers, 1, 2, 3, 4, and 5 are in recent years, right? And oddly, 2019 may actually end up being in the top 5. Again, weather whiplash. And this is a line from the National Climate Assessment. You know, we will need flexible water management strategies for a future we cannot fully foresee. How many folks here know the National Climate Assessment, the NCA? All right, you guys, this is an unbelievable crowd. So here's what I want to talk about in my talk. Current events, the obvious water cycle tied to climate change, some of the findings out of the 4th National Climate Assessment released on Black Friday of 2018 by the Trump administration, right? Trying to hit it on a slow news day. And in fact, it ended up in the news for 2+ weeks afterwards. I was one of the authors, as were 399 of my other best friends. I'm going to do a Colorado River deep dive, and then I'm going to conclude and do some closing thoughts. So you all seen this image. A couple things I want to point out, though. You can see 1998 there, right? And global warming pause or global warming hiatus, that a familiar term to a lot of you, right? The deniers really picked up on that period post-1998. 200+ scientific papers resulted. The best evidence now is that there was no pause, there was no hiatus, it was just a normal slowdown. And we should expect to see it. It will go slower and faster as the future unfolds. And 2016 was another El Nino year, much like 1998, when vast quantities of heat get released from the Pacific and warm the Earth in significant ways. And the denier community now is releasing papers that say it's cooling post-2016. I mean, we learned a lot. I mean, they pulled this in 1998 on us, and the scientific community turned upside down trying to figure it out. And so anyway, I'll just note it. Your previous panel talked about this increase in emissions, right, last year, 1.7%. Unfortunately, energy going up by US and Asia. Global energy consumption up 2.3%. China, India, US, 85% of this increase. Coal, unfortunately, up 5% in India and China, which is just stunning and depressing, right? Madeleine Albright, I heard her recently say, "I'm an optimist who worries a lot." So maybe that's what we all need to be, right? Solar deployment up, wind deployment up, and yet, and there's our Paris target. Anybody remember this event from last year, this bomb cyclone? This beautiful wind pattern, right? It looks like a hurricane. You never see this kind of wind pattern over continents, and yet it showed up. And we had record-setting surface low pressures that led to winds the equivalent of a Category 2 hurricane. An unbelievable event led to the big floods right in the Midwest. That's off at Air Force Base before and after. Here's an image of some of the flooding and the ice implicated right in this flooding, these ice dams that built up. And so what caused this? That image there is the ranks of, out of 124 years, the wetness. So the greenest, that dark green there in Tennessee is the wettest year out of 124 years of data. This is the wettest winter in US history in 2019. Again, the tide, climate change, water change cycle. And so how'd this all come about? So you have a wet winter, you've got snow on the ground, you've got rain, and then you end up with wind, and all of a sudden you have frozen ground with little capacity to absorb moisture, ice dams on rivers, levee breaches along the Missouri. We lost stored grain, we lost animals, structures, and to make matters worse, these poor farmers couldn't plant, which is, they have insurance for it, but they want to be out there growing things. Nebraska alone, $1 billion in damage, 2,000 homes, 340 businesses, and then we recently had floods in 2011 that weren't all that dissimilar. So, how many?
Could you just take one step to your right?
Yeah, absolutely. Let me just see if I can shift my computer here so it doesn't fall off. Okay. How many of you know Arrhenius, right? Swedish scientist, 1890s, first CO2 doubling experiment. All right, so that's this, 1890s radiative transfer. Here's a look at timeline for modeling components. In the 1960s, we added the hydrologic cycle in because it's so important. It moves not just water, but it also moves what? Energy. So when you evaporate water out of the ocean, as huge quantities happen every day, the energy that goes into that evaporation is actually embedded in the vapor, believe it or not. And it's that vapor, when it later condenses, that powers thunderstorms and hurricanes. So a hydrologic cycle moves not just energy, not just water, but energy. And this is a famous paper from 1974 by the two fathers of climate modeling. They did an experiment much like Arrhenius, right? They double CO2 here and see what happens. And the bottom line in the abstract says, it is also shown that the doubling of carbon dioxide significantly increases the intensity of the hydrologic cycle of the model. So scientific speak for the hydrologic cycle speeds up. So how's climate change affect this big water cycle? So where precipitation occurs, and in the American Southwest, we're going to see less to the south, especially you Arizonians, and more to the north. Where north is fuzzy and depends on the climate model. It might be the Wyoming Wind River Range, it might be further north, it might be some part of Colorado. Timing of precipitation, so when in the year precipitation occurs, the type of precipitation. I mean, everybody in this room knows we're seeing more rain and less snow, especially in the Pacific Northwest, where it already is close to 32 when it snows, and it doesn't take much to change that into rain. The intensity of precipitation. So when it does precipitate, we will see more. Imelda, the remnant of Imelda in Houston, just dumped 40 inches 2 weeks ago. And Harvey dumped 60 inches 2 years ago. And Lorenzo right now, anybody following Hurricane Lorenzo, this bizarre Cat 5 storm, the second one this year, way far east, further east in the Atlantic than anybody has ever seen a Cat 5 storm. So the frequency of precipitation, we expect more days when it doesn't, which gives us the potential for longer droughts, but then this greater intensity when it does. It's as if we have a bigger sponge now overhead. It absorbs more, and then when it decides to release it, out come these deluges. We expect evaporation and sublimation, that is the direct change from snow to water vapor, to increase more evaporation out of soils and water bodies. Plants are going to use more because it's hotter on more days and it's hotter on any given day. A thirstier atmosphere. This atmosphere now holds more moisture. That's part of this bigger sponge. We expect snowmelt and runoff dates to change earlier, shift earlier. The annual pattern of runoff, and I'll show you this later. So in western snowmelt basins, right, it peaks are typically June 1 in pre-climate change, and that's now moved 2 to 3 weeks earlier and will continue to advance. And the bummer about that is not so much the advance in date, I would argue, but the fact that later in the fall, the flows are then lower. And it leads to a longer fire season, right? Less snow on the ground, more chance for trees to burn up. Impacts on water quality. Warmer water, harmful algal blooms, I'll get into that. And then finally, there are these kind of follow-on effects like increases in fires. Dust on snow, which I'll talk about. This aridification now makes it much easier to get this dust airborne out of Arizona and southeast Nevada. And it lands on our snowpack here in Colorado. And then finally, because all water management is based on historical statistics, guess what? Those statistics are no longer as valid. And those statistics tell us how to operate dams and reservoirs, how to plan for floods, how to plan for water demands by humans. It makes it far more challenging. Both the National Climate Assessment and the IPCC have a diagram that has 10 different line graphs on it. Sometimes called key warming indicators. This is the cartoonized version of that diagram. And it just tries to put them all on one image here. And I'll note that out of these 10 key warming indicators, and they're all 10 on here, 7 of them are water cycle related. So sea surface temperatures up, Arctic sea ice area down, water vapor of the atmosphere up 5%. Glacier volumes declining almost everywhere. Northern hemisphere June snow cover down significantly, but not southern hemisphere, right? Because southern hemisphere actually doesn't have much snow cover. Think Africa, and then think also the little tiny bit of South America that has mountains. There's just not much there. That's why we don't talk about it. Sea level rise, again, we tend to think of the water cycles operating in a 2-week kind of period, but it actually works on thousands of years too, when vast quantities of water get taken out of the ocean, deposited on big ice sheets, and stored there for significant periods of time. And a good chunk of sea level rise is thermal expansion, but the other chunk is melting ice sheets like Greenland and especially western Antarctica right now, which is really flashing warning signs. All right, so here's the 4th National Climate Assessment. There are 2 different volumes mandated by this 1990 Global Change Research Act. Supposed to be done every four years. First one in 2000. The Bushies picked up the ball in about 2007 and did the second one, which came out early in the Obama administration, 2009. And then one in 2014 and one in 2018. We ended up with 2 volumes last year. And I would just want to walk us through a couple things in here. So these are soil moisture declines, and the darker colors obviously are declines, the greens are increases. And you can see these are soil moisture end of century higher emissions over North America. And I mean, just look at those brown colors, winter, spring, summer, and fall. Consistent declines everywhere, even in places where precip goes up. So if you look actually at a precip version of this, you'll see precip increasing north of maybe mid-Colorado. Increase in frequency of atmospheric rivers. No Californians here, I don't think, a few, right? So you live and die by these ARs, these atmospheric rivers, pineapple expresses, if you will, that dump huge quantities of 8 or 10 of these a year, make or break your water for the whole year. They have a Mediterranean climate. It rains for 6 months and is totally dry for the other 6 months. This actually, the water management issues in California are far more severe, I would argue, than the Colorado River in some ways, just because they have less reservoir capacity and they get whacked with just about everything. More floods, more droughts. This Mediterranean climate is really challenging. Here in this state, we can actually get precipitation in almost any month of the year. And in fact, in this state, this is the one state in the nation where you can find a precip max in every month somewhere in the state. So you go look at Iowa, it's like May. That's their precip max. I don't know if that's the exact month, but I'm just making it up. Or somewhere else in the US, it's 1 or 2 months. This state, it's all 12 months. You can find a precip max. And that partly deals with the fact that we can get weather from almost all points on the compass, including upslopes, right? If you live here, this bizarre pattern where weather comes in from the east. Increase in dry days, I mentioned this, further decrease in days with modest precip, increase in days with most precip, increase in the severity of the most damaging hurricanes. And again, this is a water cycle connection here. Higher precipitation rates, higher storm surge causes much of the new damage. And then if you're dependent on snowmelt, I mentioned the snow-covered area before, more precipitous rain, reduced western US snow water equivalent, what we call SWE on April 1. Again, less snow, more rain, and as I previously mentioned, this earlier runoff. Anybody recognize that? If you're a Californian, you might. Yeah. That's the Oroville Dam spillway after it failed in 2017. Turns out the guy who designed this was his first job out of college. One can only hope his second job was not designing a nuclear reactor containment vessel. So it's a 50-year-old reservoir, and many of our reservoirs are actually older than this, right? And so this is one of the issues, one of these weird things where, it's not just climate change, it's climate change plus something else. And in this case, it's deteriorating water infrastructure. It compounds our risk. And these extreme precipitation events can lead to more severe floods and greater risk of failure. In the Colorado River system in 1983, in a really wet El Nino year, we almost lost Glen Canyon Dam. It filled and they began to use the spillway, and 2 days later, red water came out the bottom of it. The cliffs through which the spillway go are red. Spillway is supposed to be lined with concrete. It turned out through a process called cavitation, very fast water volumes actually implode, if you will, and suck concrete away from the lining, and that's what had happened. And there was a mad rush to contain this in 1983. They actually put plywood on top of the dam, said to be the most cost-effective reclamation project ever. And were able to actually buffer it enough to not use that spillway. And they later fixed it, but there was like a 50-foot lake in the middle of the spillway. So that's one. So infrastructure design, operations, financing, again, this idea that we're really dependent on the past, they don't apply anymore. And we don't think about compounding problems, extremes, this idea of cascading failures, right? Climate change brings that all home. So water management changing future. We don't have strategies that address risk over time. Our current flood control risk rules are just like set in stone, and to get the US Army Corps engineer to change it, it takes an EIS. To give you an idea how difficult that is. It's particularly challenging for California, where these reservoirs do double duty for flood control and water supply. And that's kind of that point there. All right. So That's area burned in the west. A recent paper, it was highlighted in the National Climate Assessment. We're basically doubling the area burned because of climate change. These longer, drier, hotter summers. Note, most of these fires have some kind of human trigger. You know, if you're in California, it's your local gas and electric company, right, that's been responsible for a bunch of these. But once these areas get burning, we don't stop them. And again, another, you know, we've fought fires for so long, we now have fuel buildup in places that are not healthy. This is about water quality and quantity, and I've gone through all this stuff, and I'm actually just going to skip right through here. So let's move on. Colorado River. That's Lake Mead. Hoover Dam, largest reservoir in the US. And that white band is 150 vertical feet, length of a climbing rope, or an old style climbing rope. Represents 15 million acre feet, the annual flow of the river. The reservoir itself is a little bit more than 25 million acre feet. So that's 60% of the reservoir gone, right there. It was full in the year 2000. So here's the upper basin and lower basin of the Colorado River. Water's been allocated by 1922 compact. Anybody been to Lee Ferry right there? A few people. So here's a little fun tidbit, Udall tidbit. My sister's name is Catherine Lee Udall. John D. Lee was sent by Brigham Young to found Lee's Ferry, one of the few places you could get across the Colorado River for hundreds of miles. And it turns out John D. Lee is our great-great-grandfather. And my sister happens to bear his name. It's the same name of Mike Lee, Tea Party senator from Utah, believe it or not. You might think it's hard to be a descendant of Lee, but Lee had 21 wives. And we think there may be 800,000 Lee descendants at this point, including a terrific woman, the name of Catherine Sorensen, who runs the Phoenix Water Department, actually, who are actually really dependent on Colorado River water. So there's 7 states here, right? 4 in the upper basin, 3 in the lower. Mexico depends on this. Every major southwestern city, including those outside the basin, get water, including places like Santa Fe and Albuquerque. Cheyenne, of all places, actually manages to get a form of Colorado River through what's called an exchange. It's not physical water from the Colorado River, but they give Colorado water to somebody else where that person has access to it and take other water in lieu. If you're Las Vegas, you're 90% dependent on it, and you just spent $1.5 billion to build an intake into the bottom of Lake Mead, so that just in case the reservoir ever goes dry, you can still feed or supply water to 2 million people in Las Vegas. If you're Los Angeles, 25% of your supply goes into the LA basin. San Diego gets water. If you're Phoenix and Tucson, the river's pumped 300 miles and 3,000 vertical feet uphill, you know, showing us the old lesson that water flows not uphill, or uphill towards money, right? That's the old. Where else? I mean, if you're in the Front Range, 50% of your water comes out of the Colorado River. Here in this community, Denver, you name it, Fort Collins, Pueblo, Colorado Springs, all dependent upon water. So that's this system, 40 million people, huge amount of irrigated ag. Here, your winter vegetables, beautiful irrigated ag in western Colorado. It's really important. So let's talk about how we got to where we are. This is an image out of a paper I wrote with Jonathan Overpeck, published in Water Sources Research, a peer-reviewed journal in 2017. And the top images of the 2 biggest reservoirs in the US, Lake Mead and Lake Powell. And you can see that huge decline in the upper right there. We call the 2000s hot drought. And they lost about 40%, roughly 40% of their water in a short period of time. They're now 55% full. You can see the long-term decline in the second panel of the upper basin natural flows. Some of this is just due to the wettest period in 850 years right here, believe it or not, when they actually allocated the compact. That's kind of a big oops moment. But these declines here have a climate connection. Flat precipitation going back to 1895, and then this really strong upward trend, now over 2 Fahrenheit increase in temperatures. That's clearly related to these declines. And here's the contents. Here's just that upper right part blown up since 2000 to 2019. And those of you in Colorado know this was a big winter, right? Historic avalanche cycle. And there's what that really big winter did for the contents.
That's all the runoff that's gone down into Powell.
Into Powell, yeah. And Meade too. Well, Meade actually didn't get any of the additional. Yeah. That's all into Powell.
Wow.
Yep. So still under 50%. And, 2019 was this big water year, but it's not as big as 2011, more like 2005. And it's only 1 year after this record warm and record dry 2017-2018 year. It's unlikely to occur frequently in the future, although we will see big years. Yet another weather whiplash example. And I think everybody in this room knows, we can and do continue to set cold records, right? This year, really late runoff. And it's worldwide about 1 to 2. In a lot of places, you'll see 1 to 4 if it's particularly hot, or 1 to 10. By mid-century, I think Jerry Meal NCAR says somewhere in the 1 to 20 or 1 to 40 range, and end century, 1 to 100 maybe. But we can still set them. Lake Powell only up 20 feet. So that vertical arrow there, that green arrow, kind of takes you from August 1 of 2018 to August 1, 2019. And so just that little tiny blue thing right here, that's all that bailed us out in Lake Mead, just because 2018 was so bad. 55% of full. So here's 2018, just 1 year previous. So lowest precipitation on record Four Corners area. Record driest is that dark red bullseye over the Four Corners. And then look at the record warm temperatures, Arizona, New Mexico, even into northern Colorado, that record warm. And this is our future, right here. I mean, you invite me back, a couple of years, 5 years, I'll give you another, it'll be 2022 up here. So, it's going to become a lot warmer. And one study says, if Denver goes up by 2 Fahrenheit, it becomes Pueblo. At 4 Fahrenheit, it becomes like Lamar. And at 6 Fahrenheit, you can't even compare it to something in the state. You got to go down to New Mexico. Yeah, I love Albuquerque. I want to live there. So, we're really much less certain about these precipitation changes. And this is an older set of models, where you see kind of drying to the south, wettening to the north. Different models show that at that transition zone at different places. And what Overpeck and I predicted was by mid-century, because of these higher temperatures, up to 20% declines mid and 35% end, due to higher temperatures if precip stays flat, just because of the difficulty of talking about what happens with precip. And other Colorado rivers are going to get impacted similarly, higher water demands, early runoff. And what I haven't talked about is this idea of mega droughts, these droughts that last decades or more. And there are now multiple papers out that suggest once it heats up, the climate system is subject to these self-reinforcing cycles, and mega droughts could be part of these self-reinforcing cycles where once it gets hot, it wants to stay hot. Once it gets dry, it wants to stay dry. And while we had perhaps a 10% chance of these mega droughts in the 20th century, that number could be as high as 90% in the latter part of the 21st century. So let me talk about this one modeling study that's, again, kind of more of the same, but this warmth we're going to see is unlike anything we've seen. So those red dots are recent observations of dry years. And this image shows you from wet to dry and from cool to hot. And the cloud, the green cloud, is a whole bunch of climate models. And the blue bars show the 10 to 90th percentile of those models, so the central tendency of them. You can see that the red dots now in the 1950 to 80 period are kind of in that upper right quadrant. So dry and warm, if you will, for that time period. So here's 1980 to 2010. The red drops drop down a little bit. Notice that the blue cross has moved up just a little bit, not so much right or left. Here's mid-century under the RCP 8.5, so the real warming, the highest warming driver for the climate models. And you can see these red dots now fit down in the cool part, right? The cool and dry part. And then end century, the models can't even reproduce these temperatures anymore. It's as if they're too cool, even though they've been unbelievably hot. And that just says that. And I'll note, if you look at the blue bar, it starts to push out a little bit right into the wet period here. So as if to say, yeah, we have the potential to have these really wet years. But I'll remind you all that there's a modulation, if you will, on precipitation. There's an environmental tax before that precip or snow ends up in our rivers. It's not like the asphalt you see outside where any moisture that hits it runs off. Plants get their first crack at this. And so extra precip, no guarantee it turns into runoff. It's likely just going to turn into evaporation. So in 2016, Connie Woodhouse, Tree Ring Sciences, University of Arizona, did this paper called Increasing Influence of Temperature on Upper Colorado River Stream Flow with a bunch of co-authors, USGS and other universities around the American West. And what she did was really simple. Normalize both water year flow, so that's October to September, the way hydrologists look at a year, because that's a consistent year, right? It's one kind of weather pattern, if you will, with October to April precipitation. That's snow precipitation in the upper Colorado River Basin. And these are percentiles, so this would either be cool or low, and this would be, depending on if it's precip or flow, high or, wait a minute, I'm getting confused here. This is, so lots of precip up here, lots of runoff, and this is not much precip and not much runoff. And what Connie noticed, what she did was come up with this term called runoff efficiency. So how effective is the precip in turning into flow? And when it's really effective, she puts in a green bar or a blue bar, and when it's really ineffective or inefficient, she uses red bars or pink bars. Where are the red or pink bars? Over on the right side, right? And so what she found out is that temperature can be a major flow driver, not just precipitation like we always think, right? It turns out temperature can affect these flows. And since 1988, so right about here, all these pink lines show up. Flows can be less than expected given winter precip. And you see, for example, all these, that's precip sitting above runoff. More precip gets you less runoff, if you will. And that warm temperatures exacerbated these modest, what are really pretty modest precipitation deficits since the year 2000 or even 1998. In 2017, Overpeck and I published this thing called the 21st Century Colorado River Hot Drought to distinguish from dry drought and implications for the future. And this is the three bottom panels you've already seen. I just blew them up and just indicate the 1950s we had a dry drought with reductions in flows. You can see them here. In the 2000s, we actually have a hot drought now. And it's due to these higher temperatures. So since 2000, the river's down about 17% per year. And if you look at the precipitation records, you can only explain about 2/3 of the loss in flow. What's the other third? Temperature. That's the 1/3. And why? More evaporation, this thirstier atmosphere. And what we then said is, now these losses are about 6%. 6% being 1/3 of 17. But if you go further forward to 2050, knowing what we do about temperatures, you end up with a 20% temperature-induced loss and 35% by 2100 in some of the worst cases, if precip stays flat, which is frankly not a bad bet. Here's a bunch of different precipitations for Colorado, a bunch of projections for Colorado rivers using 2 different climate model outputs, what are called CMIP3, the older ones, CMIP5, the newer ones. CMIP5 tends to be a little wetter, hence these purple bars sit a little higher. But if you note, most of them sit, a lot of them at any rate, especially the older models, sit lower. You see these reductions in flows, and especially the further south you are in the state. So the Arkansas, for example, sits mostly below 0. South Platte, because it's in the northeast corner, right? The tendency is to be at least a little higher, especially in the CMIP5. I mean, here's Colorado River numbers, drier in the CMIP3, but still, and of course, wide ranges. And the precip right now, it's a real bugaboo, actually, frankly, to understand what these models are telling us. I mentioned this aridification idea. This is aridity index mid-century. Brown colors, of course, increases. Declining snowpack and earlier runoff, higher temps, drying soil, thirsty atmosphere, we all heard this. This idea of moving storm tracks. So we know from the paleoclimate records that as it warms, storm tracks actually want to move poleward. So in our hemisphere to the north. And that means if you have a desert to your south, like we in this state have, Arizona, thank you for your desert, that's coming our way because the storm patterns are going to move poleward. And I haven't much talked about that, but it's a pretty robust finding. Shorter winter, longer fall. Bizarrely, it might even green in this aridifying climate. We might actually see more plant growth, which is another one of these things like, wow, climate change whacks us on both sides of the head at the same time. And it's partly due to this so-called CO2 fertilization effect, the idea that these plants actually are a little more effective at water use as it warms up because there's more CO2 in the atmosphere. Megadrought I previously mentioned. You know, some people have called this the new normal. I prefer new abnormal because normal implies predictability. Abnormal, there's no, I won't say there's no, we got really good predictability on temp, but not so much on precip. There are tons of papers in the peer-reviewed literature on this. I'm not going to go through all this. This is just the latest on snow water equivalent, both the data and the models in the American West, and those red colors, of course, are decreases since 1955. And this is a measure of atmospheric thirst here. And the red colors show this increasing thirst in the atmosphere that helps drive this overall dryness. Dust on snow has been an issue. San Juan Mountains in Colorado. So dust on snow, it both reduces and advances the runoff timing. And right now, these really dusty years we think are actually 3 weeks in advance in what they would otherwise be. So here's a dusty year, a hydrograph, months of the year, volume. With dust, look, it shifts forward or shifts earlier in the year and the peak's lower, believe it or not. And the difference is about 5%. In large part because you leave the land surface free of snow, which then evaporates more during the year and actually creates a deficit for the next year. That dark surface absorbs more solar energy. That's what's driving this. And I'll note that these dust sources they're not Asia or somewhere bizarre. They're just out of northern Arizona, some grazing, land use changes, and southern Utah. So, there's a trick question in Colorado. What's the biggest reservoir in the state? And everybody, John Martin or some other reservoir, Green Mountain. No, it's Snow. And here's sort of the historic hydrograph is that dark line, the black line, months of the year. And then the purple dots there are the future hydrograph. And this is the change by month. So increases here in March, April, and May. And then I mentioned this earlier, the decreases later in the fall, right? That I think are in some ways even more problematic. This earlier melting, and 2 to 3 weeks already, and maybe even a month or more by 2100. Not much people talk about water quality, and in Colorado we have such cold water temperatures, sometimes you think it's not an issue, but it is. That's Lake Tahoe, sort of the water temperature, actually the stratification season length. You've all, I'll bet, been in a reservoir, or maybe even a swimming pool, where you get in and the top's warm and your feet's down in this cold layer. So natural lakes do this. They stratify, and twice a year the surface water cools enough that the whole thing mixes. It's a really important part of lake biology. And what'll happen actually is that we'll get these longer stratification periods. So the bottom water actually doesn't get oxygen as frequently as it did before. Higher temperatures, less dissolved oxygen, and higher metabolism for creatures. So a metabolic squeeze, if you will, for animals that live in water. And eutrophication is already a problem, right? Where these reservoirs or lakes have too much biology, too much growth going on. And it's part nutrients, I mean, that's a human problem, part temperatures and part solar energy. That's a big harmful algal bloom there in Lake Erie. I didn't have a Colorado picture, but if I'd had time, I would have gone to my nearby lake, Lake Veely, which is in South Boulder, and it's actually now got a big sign on it. Don't even think about swimming in this lake. We don't know if there's harmful algae in here or not, but there have been multiple reports in Colorado this year, stay away. Intense rainfall picks up sediment and moves it. And those lower fall flows are a problem because there's less dilution available, warmer temperatures. This is a famous 2008 policy forum, so super simple 2-page article in Science magazine called Stationarity is Dead, Wither Water Management, written by a bunch of really well-known scientists. And they talk about this term called climate stationarity, which is what water management's based on. It means the climate of the future has always been assumed to be the same as the climate in the past. Yet it's less and less true now. And we know supplies are changing, we know demands are changing, and all of our current water projects that deliver water to us now have this uncertainty around them. Good news. All right, so Madeleine Albright, optimist. So here's Seattle, and unfortunately I don't have other water systems in the West, but it's true of Denver and true of many places, actually. More true than not. There's a guy in New Mexico named John Fleck who's written a whole book on this. And so you can see population going up since 1975 and water consumption going down. So in the West, it's true. Many Western US water providers now serve more people with less water. Denver Water serves 2 million people with what they say I think is 2% of the supply of the state. So there's good news here. These systems can be reliable. It's ag, actually, that's going to be on the front line of this, frankly. This is kind of a wonky thing. We live in these states that first in time means first in right. And with these earlier hydrographs, there's a whole slug of water here on the front that was never there before. And so this opens up the potential for a whole bunch of diverters to actually get water that never got water. And they're called juniors, generically. And there's a kind of a famous study done here in this town that shows this town actually will be able to store water that they previously couldn't in some reservoirs way up high behind us in the Front Range here that they otherwise, again, couldn't store because downstream farmers wanted it. This is actually not too early to show up. And the flip side happens actually over here on the declining side. There are a bunch of diverters here who previously got water, so-called seniors, and now they're not going to get it. So it jumbles these assumptions or long-standing practices under prior appropriation. So let me close. Statewide average temperature ranks in March 2017. At the time, we had 123 years. Look at Colorado right there. Little history here. 2016, December, no snow. Come, I want to say January, it began to snow like crazy. And by March 1, the snowpack it's about 150% of normal for the time of year. Water providers were licking their chops, thinking, oh yes. Then came the warmest March in Colorado history, 9 Fahrenheit above normal. And the precipitation shut off. And 2017 just turned into like a slightly wetter than normal year. And that's sort of our future. Here's January through August, again, continued warmth in 2018. Again, I don't like the new normal, new abnormal, yes. You all know this, hotter everywhere, shifting runoff patterns, more variability, flow reduction risk. How many lived through the Front Range floods in 2013? More than a few hands. So 17 inches here in Boulder in 4 days. And I'll bet a few people in this audience actually had property damage. Billions of dollars in the Front Range. Scientists, we've had an event sort of like this in the past, but it got juiced by this extra moisture in the atmosphere. Climate change doesn't cause these events, it just makes them worse. That's generally the way to think about it. More fires, decreased water quality. If you're an optimist, opportunity for change. So there's Harvey, $125 billion in damages. So I've worked on this issue for 16 years. 1 state of Colorado assessment, 2 national climate assessments, 1 international assessment. I mean, you all know this. With each year, the threat grows. Water has been, it's going to continue to be this really big challenge just because it's so connected with the movement of energy around the planet. And, in the past 6 months, nary a week passes here without some kind of major event or often multiple events. Last week you got the climate march and you got Lorenzo going and the remnants of Imelda. And the politics on this issue are changing rapidly. In large part because people like you are doing stuff. Thank you. You all know we got the tools here. We know what we need to do. We just lack the will. And that actually gives me hope. Here's, I don't know if you've seen this climate basic. So Mike Dettinger, a climate scientist, actually gave this to me. And he had number 5, we can fix it, which is a little optimistic, and the latest version of it is there's hope, right? So I kind of modified it. And I'm going to end right there, and I think I'm pretty close to being on time. Yeah.
So we have 8 minutes for
8 minutes for questions.
questions.
I have a question here, Brad.
Yeah.
Front. About 4 or 5 years ago, the National Audubon Society came out with a couple of their modeling work with their 100 years of bird migration and habitat. And they came out with very interesting projections of which which species will be hurt, where they will migrate, what their projected extinction rates would be. You've got all this data. You could help us out if, with Citizens Climate Lobby, if you could unite with a few social scientists and make projections of the human migration that's going to take place over the next 50 years in the western United States. We've already met, I've met a few people who've moved to Colorado from Phoenix. Why? Didn't want to be that warm anymore. So is there any data that would, you've got all the models, you've got all the data, or have you ever been approached by a social scientist to do modeling of projected human migrations within the western United States?
I haven't, but it's certainly been something I've thought about, and it often comes up. I mean, I can't tell you the number of times I get calls from people, where should I move? And, you know, it's actually a hard question, right? I mean, the ideas move north, but the fire seasons in Idaho and Montana in recent years have been really bleak. And they've had 2 months with smoky weather. And we've actually in the Front Range here been mostly blessed from not having this. If you live in that smoky weather in the summer, you stink. This beautiful sky that's part of our climate is gone. It's kind of depressing. So I totally agree we need to do more work on it. Obviously dealing with the human dimension of this, what motivates people and where do they go and the like is interesting. But Phoenix, yeah, I wouldn't want to live there going forward. I was born in Tucson. I'm a native Arizonian, just for the record. Love to visit it in the spring.
Just a quick question. You had a slide of Seattle where you, I think, showed as the population rose, the use of water.
Yeah.
Water use. What were some of the things they did? I'm just curious.
So a lot of it's just been it's just been year over year efforts on conservation, believe it or not. You know, awareness, new plumbing facilities, toilets now are much better, dishwashers, people learning to take shorter showers. I mean, Seattle's a weird example a little bit because they have no outdoor watering, right? In the American Southwest, 50% of watering goes into the outdoors. And if you're clever about it, you can do things to reduce that as well. Frankly, it's not that hard because we've started in many cases from just a total wasteful, unaware, uncaring. Pricing also, I would argue, has been helpful here. This community and others have moved to almost per house pricing. How many people live in the house? How much outdoor stuff do you have to water? What's a water budget per house? That actually can help. So there are lots of tools in the toolbox. Got that roving mic there.
Okay, now I've been doing a lot of studying on selenium on my own.
Yeah.
And I'm kind of wondering, with this water deficit, how that is going to affect if it would affect, say, the efficiency of taking selenium out of drinking water, or if it would concentrate the selenium in certain places, or if the selenium, since there just isn't as much water, wouldn't be, there wouldn't be as much runoff, and it wouldn't be a problem.
Yeah, so I am no expert on selenium. And when you mention selenium, I think of some of the western Colorado irrigation districts that irrigate in these selenium-laden soils. And so they then tend to pick it up. And Reclamation and others have done multiple efforts, including canal lining and trying to reduce some of these return flows to cut these down. I mean, it may be in some places where you just reduce irrigation, the problem goes away. I don't know enough beyond that to really comment in an intelligent and thoughtful manner, and I apologize.
Somebody should thank you for taking personal initiative to do some work.
I was wondering, because you mentioned hope a couple of times, what makes you feel optimistic in your work?
Well, I mean, I can join you in the depths of darkness. If you want to go there, man, I can go there too. You know, and I'll race you. But at the end of the day, it's not helpful, right? At the end of the day, it's totally not helpful. Amory Levins quoted somebody else who said, you know, you can't depress people into action. I mean, we're humans after all, and we gotta have hope. I mean, what's hope is renewable prices that continue to drop. What's hope is having the policy tools and knowing how those work. What's hope is sort of EVs and their, you know, hopefully the coming efforts by U.S. and other automobile manufacturers. And how many people drive an EV in this? You know, I mean, it's huge, right? I mean, I own one. I mean, that gives me some hope. I get hope from the kids, actually. Greta Thunberg's unbelievable, right? And it's not just Greta, it's people on campuses and elsewhere. You know, and frankly, and this is feels a little bit like a cop-out, but women actually give me a little bit of hope too. Because and being a white middle-aged guy is it's an interesting time to be a white middle-aged guy. Yeah, passing the torch, man. Please take it. So, all right, there you go.
We'll make that our last question.